Hi everyone, it's Dr. Barden here. Today I'm going to talk real briefly about ring modulation and how we create it, what it sounds like, and some important effects that you can use with this type of synthesis. So, ring modulation gets its name from the physical arrangement of the components that would create this in hardware back, several decades ago. They were in a physical ring, and that name just kind of took from there. So that's just what we call this particular sound. So the way that we create this is very simple, and in fact, we've kind of already done it in class, which is kind of fun. I'm going to make two sine waves real quick. There are two of them. And I'll make this a little bit bigger. We don't need all of this space. So two sine waves, and I want to control them with some number boxes. So let's do some... we don't need to worry about floating point values. So this will control the frequency of the sine waves. And then eventually we're going to head to a gain and then out the output right there. Like so. So this is most of our modulating setup here. So we've got two different sound sources, and when we're modulating sound, which we are changing an aspect of it. So what we're going to do with the ring modulation is we're going to take the amplitude of one sound and modulate it, change it based on the amplitude of another sound. That's a very wordsy way of saying that we're going to take the value of every sample of the audio stream and we're going to multiply them together and combine them. So we're going to just go like so. The math operators always take a second to load on my computer. But we're going to combine it like this, and this will be our ring modulation. So we have two different sound sources. We are multiplying each of the values every sample together. What this is going to cause is the sounds to interfere and propagate in unique ways. And we'll hear it in a second, but essentially the combination of those values, some of the frequencies will cut out, others will be reinforced, so we'll hear new sounds that weren't part of the original parts. One way to think about it is if you were to just combine these together, if they were both equal to 0.5 at that sample, if you add them up, you get 1. If you multiply them, you instead get 0.25. It's a very different value. So, again, that's just one way we can combine that. Let's just create it first, and then I'll talk about it a little bit more. So I've got sound going, and I'm going to set this to just 500 hertz on both of them. 500 hertz. All right, so we hear 500 hertz. That's great. The reason we are is because every sample, it's the same, so we're just, it's multiplying by itself. We just hear itself. But let's change this value here. Let's set it to 600. I'm going to do 700. 800. 200, why not? I'm going to turn that down while I talk. So that's generally what it sounds like with sine waves. What is happening, though, is that by combining these two frequencies together, with those numbers all being multiplied every sample, we're going to build up two frequencies that are related to the relationship between the original. So you can think of this one over here as the what we call the carrier frequency, the main pitch, the starting point, and this one over here, the modulating frequency. This is what is changing the other. And the distance between these two is what those side bands that we hear are. If you hear the low and the high frequency that was playing whenever I changed this number here, those are the side bands. It's neither 500 or 200, but rather it's a little bit different. So what those bands are, you can think of it as the sum and the difference of these two values. So if 500 is the carrier frequency, then the pitches we're actually hearing are 200 above and 200 below 500. So if you add them together, you get 700. If you subtract them, you get 300 hertz. So if I turn that up, we should hear 7 and 300 hertz. That's what I would call that. If we did... let's see here. Boop-a-doop-boof. We combine them at, let's say, 500 and 600 here. With things get a little weird because technically you can't have negative 100 hertz. So at this point, the 600 becomes the carrier, and we are hearing 500 above it at 1100 hertz and 500 below it at 100 hertz. So again, this just, you're adding and subtracting them from each other. You hear those two tones. That's all ring modulation is. By combining two different sound sources together, by multiplying them, you get the combination and the side bands of all of those combining frequencies. So you can use any sound source for this. If I went in here and let's make this one a saw wave, and let's make this one a pulse wave, a square wave. Why not? Oh, is it not pulse? It's rect. The square wave. What does this sound like? I'm gonna also set this to and 200 here again. Let's go 400. Got angry at me. Okay, that surprised me. It had to get reinitialized, but here's the same modulation, but with much noisier, aggressive sounds. So they can be completely different oscillator types. We could, throw on a subtractive synthesizing, filtered out noise could be one. We could do an audio file. So let's, I've got a lot on here. Let's find a longer one. I just have too many sound files in my Macs to find things. Let's... That'll be one of them, because I know that won't be copyrighted. And we'll do that one in Anton. Why not? Oh. Helps if you unlock the patch. Anton and trumpet. A3. So we can utilize sound files or recorded signals, any two audio signals we can ring modulate together. So let's replace the rect with this sound file. If we turn that, lock this, turn it up a little bit, play the sound file. I'll turn it up a little more. We get this really weird, very grainy, sawtoothy rendition of that Anton file that you hear. So that's interesting. If I were to replace that with the trumpet A, we'll have a similar thing. That one's a little more closer to what we heard before because this is just a trumpet holding out a pitch like the saw wave. Or we could, if I up in here, we could replace, modulate a sound file by another sound file. If I start these, I'll just turn one on. So we get just interesting combinations of sound files where you get characteristics of both of them in there, but for all of the frequencies in that signal, you get those two sidebands. So you could change what sidebands are happening by offsetting the signals from each other. So if this changed notes, I could play it from a different point and change what the sidebands are. You can really combine things in a lot of interesting ways and make interesting timbres that you can then save or sample or use as an instrument. It's just a fun way to make sounds. A quick side note: if you are using audio files that you do need to you do need to see if there is any silence in the audio file. If there is any point where the audio dips out, you're going to have a dip out in your signal. If any of these equals 0, multiplying anything by 0 is 0, so no sound. So if any of your sound files have silence in them, that will have silence in the end results. So the last thing I'll mention is that, again, you could think of this as a synthesizer in and of itself. So we'll use this as our synth, and what we can do is just wire this in to an envelope. Line tilde. And we'll add them together, or not add them, but multiply them together to create said envelope. And we can say, dollar, this is $1, 50. Why not? Milliseconds. Oh, wait, that's going to be weird. Sorry, I should change this. So we should line and set it up this way. So we will message start at 0, go to 0.9 over 50 milliseconds, go to 0.8 over 50 milliseconds, go to 0.8 over 500 milliseconds, go to 0 over 100 milliseconds. We'll see how that works. And then if this goes into here, now if I lock that, we play these. I've added just an amplitude envelope to the sound here, and with the sound files, it's a little weird, a little random because they're at different points when I trigger them. But if I were to instead wire back in our our oscillators instead of our sound files. No. And then there we go. So there's our particular pitch and timbre. So every time we trigger it, we get that. We can change this. And get a lot of different sound options. So this could be an instrument to play with, and you trigger your sounds whenever you hit a key. You could send MIDI notes and frequencies, all kinds of things. You could have these numbers automatically respond to things being generated in Max or be random. There's a lot of ways that you can just create values for frequencies, and then all you're doing for ring modulation is multiplying them together, and the end result is two frequencies, but neither of them being the original one. Instead, it is the pitches you hear are the two frequencies added together and the two original frequencies subtracted from each other. So in this particular case, I'm going to change this so I can do easy math. If this was 900 and this was 200, then the frequencies we will hear are 1100 and 700 hertz. Sounds like it to me. Envelope I made sounds a little crunchy, but that's on me. Then if you treat this as an instrument in a sound generator in and of itself, you can add it into a simple envelope and trigger it just like any of the other instruments we've made before. So that's what I've got there. Last thing, again, you can use any audio signal. It does not have to be an oscillator. In fact, you sometimes get really cool results with it not being that. So that's all I've got now for real on this. There's going to be a max patch of just a really basic ring modulator in the Canvas page. So check that out. This could be something that you use for your instrument on the max patch assignment. So if you have any questions, send me an email, stop by my office hours. You know the drill at this point, and I'll see you next time I see you. Bye.